Hi, I'm Lingduo, and my topic is magnetic imaging with quantum sensors. In conventional imaging, optical microscopy is normally used because it easily achieves resolution close to the optical wavelengths. But from the Rayleigh criterion, we know that diffraction limits the resolution to about half the wavelength. Recently, it was shown that the limit can be partly overcome by nonlinear imaging techniques, but there is still a barrier to reaching the molecule scale. In contrast, in magnetic imaging, the spatial resolution is not determined by diffraction. Rather, it is limited by magnetic field sensitivity, and so can in principle go well below the optical wavelengths. In the past, the sensitivity of magnetic resonance imaging has been improved enough to image single cells and has succeeded in detecting single electrons. Although such approaches continue to deliver amazing insights, they also suffer from drawbacks such as limited temperature and magnetic field range, limited spatial resolution. The new applications that overcome these limitations are highly sought after. The field of physics has recently discovered diamonds as an ideal material for magnetic imaging. The usefulness of diamonds is based on two properties. First, defects in diamonds are often characterized by low electron-phonon coupling, mostly due to the low density of phonon states. Secondly, color center in diamonds are usually found to be very stable, even under ambient conditions. This makes them unique among all optical active solid-state systems. In past decades, color center in diamonds, which are fluorescent lattice defects that consist of one or several impurity atoms, have been intensively studied, and physicists have made tremendous progress in understanding and controlling the electronic property of single impurities. One of these impurities, the nitrogen vacancy defects, also known as NV defects, is furthermore magnetic and shows quantum behavior up to room temperature. While nitrogen vacancy would be the special impurity, negatively charged nitrogen vacancy centers in diamond have been proposed as a sensor of measuring individual spins because they have long coherent times. Moreover, because NV centers are atomic in size, they offer significant advantage in magnetic resolution and sensing capability even at room temperature in some systems. Now let's look at the spin property of NV centers. The two triplet states are further split into three spin sublevels. Because of axial symmetry of the NV center, the two ms equal plus minus 1 states are degenerate, and the ms equal 0 state is energetically lower. The energy difference between spin sublevels is d equal 2.87 GHz for the ground states and d equal to 1.42 GHz for the excited states, where d is so-called zero-field splitting. The degeneracy between ms equal plus minus 1 can be lifted by a magnetic field, causing the ms equal plus minus 1 level to shift in opposite direction. Optical transitions are strongly spin preserving, means that the spin states do not change while cycling between ground states and excited states. This magnetic field dependence forms the basis of all magnetic sensing applications. Then, how can we get results from the NV center? We need to perform electron paramagnetic resonance experiment on a single electron spin. The most basic experiment is to record the EPR spectrum of the NV center by slowly sweeping a microwave field over the EPR resonance. At the microwave frequency, is resonate with EPR transition. Excitation from ms equals 0 to ms equal to plus minus 1 occurs, resulting in a reduction of fluorescence intensity. This so-called optically detected magnetic resonance effect is characteristic of NV centers and has only been observed for a handful of other molecules artifacts. The ODMR effects provides a means to modulate the fluorescent intensity dependent on the magnetic interaction of the spin electron. The magnetic field sensitivity is easily recognized from figure D and E. As a magnetic field is applied, two resonances appear in the ODMR spectrum because the degeneracy between the ms equal plus minus 1 level is lifted. The frequency separation between the two resonances is given by 2 gamma Bz, where gamma equal to 2 pi times 28 GHz per Tesla, and Bz is the magnetic field parallel to the NV axis. Thus, measurement of the ODMR frequency immediately yields the absolute value of the magnetic field. This principle of magnetic field sensing is well known, while the particular exciting aspect of the NV center is that similar measurement that can be performed on single spins that are localized within a few angstrom. Now, let's look at one specific applications of magnetic imaging. Scanning probe microscopy offers an exciting perspective to push the spatial resolution of a diamond sensor towards atomic scale. The basic idea is to embed an NV center at the apex of a very sharp tip, and to scan this tip over the sample of interest. Because the spatial resolution is defined by distance between the tip and the sample, very high resolution image can be recorded. For scanning NV sensors, the minimum tip sample distance is limited by how close stable NV center can be formed to a diamond surface, which is currently approximately 2 nanometers. Several exciting experiments have recently been reported using scanning magnetometers. Figures show some examples, including the imaging of a magnetic vortex in a thin ferromagnetic field and the detection of a single electron spin at a distance of approximately 50 nanometers, and the image of a nanoscale magnetic tip with a resolution exceeding 10 nanometers. Finally, let's discuss the main obstacle towards better diamond probe: surface effects. Stable NV centers have been observed at a minimum depth of approximately 2 nanometers from diamond surface, and in nanocrystals as small as 4 nanometers. At this shallow depth, surface property can greatly impact the electronic stability and the spin lifetime of the defects. Despite the expense of electronic wave function of the NV center being less than 1 cubic nanometer, no NV center have been reported for such small crystal. The main issue with shallow NV center is the conversion to neutron NV. The mechanism behind charged state conversion is not entirely clear, but appears to involve either stable charge trap on the surface or surface bonding. For very shallow NV centers, loss of charge may also occur via quantum mechanical tunneling.